Yeah, thank you very much for this invitation. I enjoyed very much to stay here in Norway with this hospitality we find here. And it is a great pleasure to participate in this conference. Yeah, as you see, my compliments particularly to the organizers of this conference, which shows we are on the scientific pathway and not following here the mainstream here. Nevertheless, this is a scientific rule. Some of us are using a slightly different pathway, and so we have to see what may be the right physical basis of this. Yeah. But before I go into details, which is a real challenge, thank you, Ferdinand, to respond. I have a little bit different data. I would like to say one sentence as actually the editor of the journal Science of Climate Change. For all speakers, it would be a great pleasure if you can afford to supply a summary, typically about 5 pages maybe, as your conference contribution, which we will sum up and bring out as a special issue of this conference. Is this in your sense? Yeah? So this was our suggestion to do this, and hopefully all the speakers can manage in this way. Thank you. Now, I'll briefly mention and go into some rough details of the IPCC's explanation of the CO2 increase, and I'll try to show even the difference between, when I understand right, Ferdinand can correct me, the difference of IPCC to the CO2 coalition, and I will oppose this to my own understanding. Now, despite dramatic, I really have to stress this, dramatic changes over the Paleozoic with 10 degrees temperatures, or some people are even talking about more, and with CO2 concentrations 15 times higher than today. Yeah, with the inception of the industrial era here, for many climate scientists, and in first position of the IPCC, but also the CO2 coalition, I have to say, natural impacts almost no longer exist. Now, instead, we hear almost only fossil fuels are responsible for any CO2 increase. And the IPCC additionally alleges that at least 90% of temperature increase is caused by this greenhouse gas. And that's the reason that this is an important discussion about the contributions of CO2 in the atmosphere. I'll concentrate only to this first point here. Now, before 1850, the carbon cycle, we heard this just beforehand, was in balance with atmospheric CO2 concentrations of about 280 ppm. This is some repeat. Most of you are familiar with this, but to give a brief summary of all these aspects. So, additionally, we have some in and out fluxes of 80 ppm per year. Now, over the industrial era, this has come out of balance. That's the interpretation of the IPCC, with nowadays 424 ppm, 145 ppm more than in 1850 or 1750, almost the same. And additionally, additional fluxes due to the fossil fuel emissions of 32 ppm per year. Now, human emissions are contributing, as we know from the CDIAC data, 5.7 ppm per year, actually, almost actually, which is 5.1% of the total emissions I mentioned beforehand. So, and from these, 54% of these emissions are almost directly absorbed by the oceans and by biosphere. The other part, the so-called airborne fraction, with 46%, is accumulating in the atmosphere. That is the idea, that is the picture. And this is made to be responsible for the increase of CO2 from 280 to 425 ppm. The removal of these additional 145 ppm, that's the idea of that's the numbers from the IPCC, take several hundred up to 100,000 years, described by different adjustment times. We heard about adjustment time just beforehand, but this is even differentiated in different adjustment times by the IPCC. There is, as we see, this first a difference to the CO2 coalition. Now, the removal, the residence time, or other people call this the turnover time, is all okay. Yeah. So the residence time as the ratio of the actual CO2 concentration divided by the in or out fluxes is this 3.8 years. So far, some remembrance. This is here as a small sketch summarized in this figure here, where we see this is a strange situation. This is called the so-called airborne fraction model of the IPCC, and well suited to convince political policy makers. Yeah. So there we have in and out fluxes between the natural and the anthropogenic emissions here circulating around with about 4 years. Some people even differentiate and cut this, that they say only the natural emissions here are circulating and the anthropogenic emissions are separated and accumulating in the atmosphere. On the other hand, we see that here the new emissions are one part, 54% are directly absorbed by the oceans and biosphere, and the other part is accumulating in the atmosphere. When we write not too special, but to write this as a balance equation, then we see we have here the changes of CO2 per year as the influx minus the outflux. The outflux is that what goes this way, as you see here. And when you calculate this, this is just here the airborne fraction times the emission rate. So, and indeed, summing up this over many years, this gives an excellent agreement here with the Mauna Loa curve. No discussion about this. Yeah, and this confirms an airborne fraction of almost 46%. Okay. more advanced model, the so-called Bern model, especially preferred by IPCC, even uses time-dependent airborne fraction, which we can name a pulse response function, and using 5 different adjustment times. Again, the adjustment times from, as you see, from infinity here, 18% are staying in the atmosphere forever in this model, and a faster decay here with 3.4 years. Also, this gives, with some adaptation, you can get good results. You can good agreement here, as you see, also with the Mauna Loa curve. This lower graph is the emission rate, which together with this pulse response function gives a convolution integral. Okay. Now, but at least for me, there exist some principal discrepancies, yeah? And when we look first, a constant natural cycle neglects all additional native emissions which have been observed over as far as people recognize and collect all this data. We know that we have some variations. This contradicts paleoclimatic and actual observations. 46% of new emissions in the Bern model, I mentioned 18% are accumulating forever in the atmosphere. Other fraction, other contributions instantaneously are absorbed, but no uptake of the previous accumulated emissions. How can this work? The addition, only the new is directly absorbed, and all what was already accumulating is not influenced by any process. So this violates the equivalence principle, and the system never comes to an equilibrium, not to a previous one or a future equilibrium with a further constant emission rate. Yeah. The absorption is assumed to be proportional to the emission, not to the concentration. That is the main point. Since all what we know about natural systems, we see this is a clear descent to native decay process, and the observation also of the C14 decay, I mentioned this afterwards. The total CO2 content, or only the native part, is exchanged within 4 years like an inert gas, yeah, but no real absorption and emission at the surface. Even when Ferdinand is talking about the absorption in the North Atlantic, for example, in the polar areas, and coming up thousands of years later in the equatorial areas. So this, there is a lot of compounds. The CO2 is absorbed, is changed into chains, into organics, completely different. Yeah, but it is not only a circulation going up and down and going up and down. So now the more elaborate Bern model, as I mentioned, these 5 different absorption channels are assumed also proportional to the emission, not to the concentration. And even worse, they are assuming these absorption processes, when they even assume absorption, they are working in series, so determined by the smallest hole in the back, and not by the parallel absorption processes. So, okay, what is the difference to the CO2 coalition and some other groups who are discussing explaining most of the CO2 in the atmosphere by human processes. Now, they overcome some of these problems. Indeed, they're assuming an absorption process proportional to the actual concentration. But the problem is to separate this into a natural cycle where this is absorbed independently, and another cycle or another world in which this happens only determined by the excess concentration, which is the actual CO2 concentration minus the concentration at 1850, where they use here a time constant. This is identical, almost identical, with the turnover time, or what I call the residence time, of 3.5 years, as we see here. And then these two terms cancel. They have no contribution in this equation. And anything is only determined by this excess concentration, but with another time constant here, as we see, of 45 years. You were talking about 50 years, a little bit different from one group to the others. So to fit this quite well, I have had to use these numbers with 44 years, and this people call adjustment time. For me, this is nothing else than a second residence time. And instead of an infinite accumulation, indeed, this is a difference here. We have that the system is approaching for a constant emission rate to this concentration at 1850 plus the emission rate and multiplied by the adjustment time. So also this gives a good agreement, and we see an urban fraction oscillating around 45–46%. But excluding here this term, and otherwise afterwards telling only the anthropogenic emissions determine this increase, this is, for my understanding, this is circular reasoning, and it also violates the equivalence principle. Now, these are different reasons for a more realistic approach in agreement with all observations and physical causalities, as we call this. My studies here, these studies arose from a close cooperation with the late Murray Selby from Macquarie University in Sydney. And our approach includes a temperature-dependent natural emission. I call this EN as a function of temperature, big T, and time, and an anthropogenic emission, EA, over time, over the industrial era. The absorption rate is proportional to this, the absorption rate, what is going on here, the same problem as we had before here. I thought I could avoid this. The absorption time we see here, the absorption process is now not the concentration and the difference to 1850 as the excess concentration, but it is the real actual concentration CO2 over an effective absorption time, as we call this. This gives the conservation law with the input, native input, anthropogenic input, minus the absorption proportional to the actual CO2 concentration. only using one time constant tau effective. Now, as a confirmation of this conservation law, and also for a deeper, better understanding of the uptake of CO2 in the atmosphere, we can look to C14 as an ideal tracer for this absorption process. So in the stratosphere, we have with the incoming cosmetic radiation, as here identified by some neutron, we have some excitation process that nitrogen nucleus is colliding with the neutron and kicks out a proton. The C14 is rapidly oxidized, and we find a concentration of not more than about 10 to the 10% in the stratosphere. This is relative to the stable isotopologues. The radiative lifetime, as we know, or here better just the enfolding time, is more than 8,000 years and much larger than any time we have to discuss on this in this relationship here. Due to the nuclear bomb tests up to 1963, we had almost a doubling of the CO2, C14 concentration in the stratosphere. Yeah? And so with the stop of these tests after 1963, we can look to the relaxation of this process of the uptake of C14 by the external reservoirs. And the typical quantity which is measured is the C14 anomaly or delta per mil value presented as the relative difference to this C14 as a reference times 1,000 and presented in as per mil, delta per mil value. So this is one check and also explains a bit about this process. Here we see such a measurement at Vermont in Austria about the decay of C14 after 1963. And we have this exponential decay and fast oscillations over the very first 5 to 6 years. Often these oscillations are neglected, but they give a much deeper insight and understanding for the absorption process. And the reason is that these fast oscillations come from Brewer-Dobson circulations from the stratosphere into the troposphere, and particularly in boreal winters. Now, we consider a 3-volume system to reproduce this decay process, also with the faster oscillations. And when we have a mass volume here, delta M14, which is transferred to the troposphere, then the concentration in the stratosphere is reducing by this ratio, which is where MST is the mass in the stratosphere, and on the other hand, the mass in the concentration in the troposphere is increasing by this fraction divided by the mass in the troposphere. And the same happens here between the troposphere and the surface. So this gives a coupled differential equation system which can be solved and try to understand. And so the solution is here shown for the aim normally of the CO2 concentration, the C14 concentration in the stratosphere here decaying, but this from there everything is with the higher concentration is step by step shifting and going to the lower levels. Here we have the good agreement with the measurements in the troposphere, and the red graph shows the calculated concentration in the surface. Now we get this fast oscillations and fast uptake, which can even be from these calculations and comparison with the measurements of only 8 months, not more. Yeah, and on the other hand, this slows down to approximately 8 years over longer absorption times. So, and this we call the effective absorption time. What is the effective absorption time? Now, when we only look for the equation for the troposphere, we see that we not only have this decay term, but also some additional injection emission. We call this the re-emission from the surface to the troposphere back, which is proportional to the concentration of C14 molecules in the surface layer. But this can well be approximated for our discussion here as some fraction of the concentration in the troposphere as a fraction better, and then we have an effective absorption time, which is defined in this way. Now, when we take the same model and calculations also for the anthropogenic emissions, then we see that, and we are using the carbon dioxide information and analyze center data for the emission of anthropogenic emissions over the years from 1960 to 5 here. The rest here is some extrapolation for, as we just see in a moment. Then we get for the stratosphere this yellow or orange graph, for the troposphere this blue graph, which are close to equilibrium, and this for the surface. And we see with increasing time, and this means due to the additionally increasing emission of anthropogenic emissions over the years, this is coming. This gap is magnifying. So, and the reason is the difference to the C14, that we now have an injection of C14 directly to the troposphere, and this is a continuous process which results in a magnification, a magnified disequilibrium between the surface, and this inhibits the offset of direct absorption. So, in other words, this process is responsible that even under these conditions, we can have a shorter time than 8 years as found from the C14. Yeah? This strongly depends on the assumed mass ratio of the troposphere to the surface. And for a quite conservative assumption of only 1/4 between troposphere and the surface, we find that the anthropogenic concentration of CO2 is about 13 ppm, which is 9% of increase over the industrial area, or when we compare this to the total CO2 concentration of 425 ppm, this is only 3%, yeah, which is caused by the anthropogenic emissions. And we also see when we have a constant emission up here since now, 2025, no further increase, then the anthropogenic emissions in the troposphere are only increasing by 1 additional ppm, not much more. Okay, but you can trust this, and ask, what is he talking about? From where is this kind of other necessary CO2 coming? Now, how do we explain the much larger increase of CO2 over recent decades? The surface processes here, like emission and absorption of CO2, depend intrinsically about temperature. We can talk about size, that's a question, but there is no question that there is some relationship. We see this also in the ice core data. So, seasonal emissions in the uptake are almost 6 times larger. These oscillations we see on the Mauna Loa curve are 6 times larger than the anthropogenic emissions. We have soil respiration, which is even increasing exponentially with the temperature. Or we have emissions and uptake by the oceans, of course. So, different to the IPCC, we don't ignore biosphere, we don't ignore the oceans, and not the permafrost. Thank you. So, as a result, we see also we have to include the many non-observable, almost not observable volcanoes, and we have estimated 1 million submarine volcanoes, from which thousands of them are expected to be active. So, as a result, we look to the Mauna Loa curve as a good reference, and we see the oscillations here from year to year are reproducing quite well, and what additional emissions can be expected? Yeah, okay, we look closer to this Mauna Loa curve, and when we have the average over one year, and we look closer to this average curve and make the derivative, that means the changes from one year to the next, then we get again the balance equation here with the native emissions, the anthropogenic emissions, minus the uptake. So, and this we call the net emission rate. This net emission is shown here as a blue graph. And we see here this trend, and we see a lot of oscillations, which most of them are coincide with El Niño events. And we see this increase, which is about 2 ppm per year over 65 years. Somebody may say very, very small, but what we are talking about is the difference. This is the net emission rate and not the direct emission. So, and therefore, we can, having this picture in mind, we can now look to the sea surface temperature, or also the land surface temperature, taken from data from satellites and also from sea surface data, and then we see this kind of graph. And also here I have to mention particularly over land and sea. We see this well represented by the SSTI measurements, and again these spikes coincide with the El Niños. That is a good reason to at least look more carefully if there is some relationship between each other. And now here we see again the previous measured the result from Mauna Loa, the derivative, and I should mention generally these emissions over sea and land result from measurements over sea and land, but the outgassing from oceans is much lower than from soil respiration. About 1 order of magnitude difference. Yeah. So, and particularly in the tropical areas where we saw this time-dependent behavior, there we have also the strongest emissions in these tropical areas. So, and when we calculate this with this small exponential increase, not very dramatic, but the main difference is already these numbers here, we get as calculation a closely tracked situation with about 80% correlation. So, let me also note, the emission is in phase with the temperature. The emission that is the derivative of the CO2 concentration. The concentration has a phase delay of 90% to this. And this we see already from the standard work, I would say, from Ole Humlund, Kjell Stordal and Jan-Erik Solheim about their correlation measurements between temperature and CO2. And at the same time, almost at the same time, this was published by Murray Selby. So the CO2 cannot be the reason for this temperature increase. So finally, we come to this graph here. This is the measured Mauna Loa curve with the seasonal oscillations. And we have to integrate our emissions I was talking about beforehand here in this term, including also these seasonal oscillations and considering the anthropogenic emissions. The result is shown here as a magenta curve, which almost completely covers the measurement, as the blue behind, and the green is the calculated CO2 concentration due to native emissions. The respective anthropogenic emissions are shown here as the blue graph, light blue graph, with, as previously mentioned, with 13 ppm to 145 ppm gives about 9% as contribution, or directly compared to the actual CO2 concentration, not more than 3%. Yeah. The lower graph is the CDIAC data, the emissions, which are found from all the fossil fuel emissions. And this is a ratio, as previously mentioned, 5.7 ppm to the 112 total emissions gives 5.1%. So at least when we don't trust these calculations with this magnified separation between troposphere and surface and an even shorter efficient absorption time, we can expect as an upper limit that the emissions, the anthropogenic emissions compared to the total emissions with these 5.1% determine the contribution of nature, of humans compared to the nature. So with 5.1%. In summary, let me say, only briefly, maybe as also entrance to our further discussion, the coalition team, as I mentioned, uses this balance equation with these numbers determined only by the excess concentration, which determines the airborne fraction and gives this yellow graph for the airborne fraction. For constant emissions from 2025 here, this approaches equilibrium in about 100 to 150 years. Yeah. Okay. The difference, my approach here is we use balance equation for the native cycle and the anthropogenic cycle with this excess concentration here for the concentration, but with one unique absorption time or residence time, how you may call this. So, and let's only, as a simple example, consider, finally, we consider stable anthropogenic emissions, no changes up to now, or even previous a few years beforehand. So then only native emissions can determine this airborne fraction. This is 0. When we assume a native emission, which is continuously increasing by this straight line here, by this straight line, delta times t, yeah, we get as a first approximation this magenta graph. And we see that the airborne fraction here is stable 45%. No anthropogenic emissions assumed, only native emissions. So this was always a claim also for the CO2 coalition. There can be no native emissions in the system responsible for any increase. Okay, but this is not very good fitting here. We can improve this, and what we here see, this difference here can be approximated, only by this increase. That is nothing else. That is important now. There is nothing else than the derivative of the native emissions, and this derivative times the time scale here. This gives over the effective time gives the contribution for the airborne fraction. Okay, when we assume the real emissions, the anthropogenic emissions due to the CDIAC data, and we also include the native emissions due to this temperature increase, then we get this curve here, which completely overlaps with the Mauna Loa data, and we get here this airborne fraction around 45%, of course, again. And what we also see is that in this realistic case, we see that the native emissions were increasing from originally about 80 or 79 ppm per year by 27 ppm per year, which is 7 times more increase than the anthropogenic emissions over this period. So, where this hurts or violates the balance equation? I don't know. I don't see. And finally, to mention this also, since in this discussion this is also always discussed that you have this CO2 increase, and when you shift this term to the left side, then you can, with this well-known two values, you can also determine the difference on the right side. And from this follow that nature is a net sink. Okay, this we do here only for the airborne fraction, or you can multiply this with EA, then that's this original equation. This term comes to the left side, and we see that the airborne fraction here, or this equation, is only determined, mostly determined here by the by the changes of the native emission rate over the effective time, and this is compared to the total CO2 uptake of the anthropogenic emissions, and this is always. This term is much larger than this term, therefore all this is negative all the time. Therefore nature is a net sink. Nevertheless, due to this result, nature is a net sink. Nature nevertheless is the main emitter for the increase of the CO2 concentration. There is no difference. So, what we found, carbon cycle is controlled by a first-order absorption process acting equivalently for native and anthropogenic emissions. So the effective absorption time is not longer than 10 years, but can even be shorter than 3 years. Despite the significant native growth rate of 27 ppm per year over 65 years, as we found, nevertheless is the airborne fraction smaller one. And nature can be a net sink. No discrepancy between this. With anthropogenically caused CO2 less than 10% and a global warming over industrial area of CO2, as this results from own calculations due to radiative transfer calculations and special modeling, due to the impact of the sun, we find that this is not more than over the anthropogenic, over the industrial area, not more than 0.3 degrees. So humans are responsible for a global warming, this less than 10%, and this value then 0.3 degrees, 0.03 centigrades. So, to further reduce this absorption, absolutely negligible contribution, we endanger a secure energy supply, as we heard this just in the previous talk. Yeah? And this is destroying our standard of living, as we see. Thank you for your attention.